When people ask me whether reality might be a simulation, I start from the same place I start with any big question. I ask what we can actually measure, what we can test, and what the universe is already telling us through data. I do not begin with computers. I begin with gravity, space-time, dark matter, and dark energy, because those are the parts of reality we see acting on the largest scales. If reality is like a simulation in any meaningful sense, it has to reproduce these things with extreme precision. So I want to walk through what we know about the universe, how we know it, and where the gaps are. Only then can we talk honestly about what it would even mean to simulate such a universe. I start with gravity because it is the simplest to feel and the hardest to escape. For most of human history, gravity meant falling apples and orbiting planets. Newton described it as a force between masses. That worked well enough to send spacecraft to other planets. But in the early 20th century, Einstein replaced this picture with something deeper. In general relativity, gravity is not a force pulling at a distance. It is the curvature of spacetime itself. Matter and energy tell spacetime how to curve. Curved spacetime tells matter how to move. This is not a metaphor. It is a precise mathematical framework that makes clear predictions. We know this model is right, at least in the regimes we can test, because we see its fingerprints everywhere. The orbit of Mercury precesses at a rate that Newtonian gravity could not explain, but general relativity predicts it correctly. Light from distant stars bends as it passes near the sun during an eclipse, exactly as curved spacetime demands. Time runs slower near massive objects, a fact we have to correct for in GPS satellites, or your phone's navigation would drift by kilometers each day. We see gravitational redshift, gravitational time dilation, and gravitational waves from merging black holes. These are not vague patterns. They are specific quantitative matches between theory and observation. If reality were a simulation, any underlying system would have to reproduce all of this structure. It would need to generate a four-dimensional spacetime with Lorentz symmetry, where the speed of light is the same in all directions, and where mass-energy curves that spacetime according to Einstein's equations, at least to the precision we have tested. That alone is a huge constraint. We have probed gravity from millimeter scales in the lab up to billions of light years in cosmology. We have not found a clean, obvious break where gravity suddenly behaves in a way that would scream, "This is a cheap shortcut." But gravity is only one piece. On the largest scales, we see not just curved spacetime, but an entire universe that is expanding. We know this from the light of distant galaxies. When we measure their spectra, we see absorption and emission lines shifted toward the red end of the spectrum. The farther a galaxy is, on average, the more its light is redshifted. The simplest and most consistent interpretation is that space itself is stretching. The wavelengths of light are stretched along with it. This is not like galaxies flying through static space. It is the metric of spacetime changing with time. We can measure this expansion rate. Today we call it the Hubble constant. There is some tension between different methods of measuring it, which is an active area of research, but the basic fact of expansion is not in doubt. When we run the equations of general relativity backward in time, using the observed matter and radiation content, we find that the universe was once much denser and hotter. That leads to the Big Bang model. It is not a bang in space, but an early phase where the entire observable universe was compressed into a much smaller volume, filled with a hot plasma of particles and radiation. We have direct evidence of that hot early phase in the cosmic microwave background, the CMB. This is a nearly uniform glow of microwave radiation coming from all directions in the sky. Its spectrum is an almost perfect black body at about 2.7 Kelvin. It is exactly what we expect from a universe that was once hot, dense, and opaque, and then cooled and became transparent about 380,000 years after the Big Bang. We see tiny temperature fluctuations in the CMB at the level of about 1 part in 100,000. Those fluctuations are the seeds of all later structure, the places where matter was slightly denser and later grew into galaxies and clusters. The pattern of these fluctuations, their sizes and amplitudes, contain a lot of information. They tell us the total density of the universe, the fraction in ordinary matter, the fraction in something else we call dark matter, and the amount of what we call dark energy. These are not arbitrary names. They are placeholders for things we infer from their gravitational effects. Dark matter is the first of these invisible components I want to unpack. We discovered it not by seeing it directly, but by noticing that galaxies and clusters do not behave as they should if only visible matter were present. When we measure the rotation curves of spiral galaxies, we find that stars far from the center orbit at nearly the same speed as those closer in. If only the visible stars and gas were there, the outer stars should orbit more slowly, like planets in the solar system. Instead, the rotation curves are flat. The simplest explanation is that there is extra mass in a large, roughly spherical halo around the galaxy. This extra mass does not emit or absorb light in any obvious way. We call it dark matter. We see similar evidence in galaxy clusters. The velocities of galaxies inside clusters are too high to be bound by the visible mass alone. Gravitational lensing, where mass bends light from background galaxies, also shows more mass than we can see. The CMB fluctuations require a certain amount of matter that behaves like pressureless dust at early times. All lines of evidence converge on the need for a dark matter component, roughly 5 times more abundant than ordinary matter by mass. We do not yet know what dark matter is. It is not made of protons, neutrons, and electrons in the usual way, because that would conflict with measurements of the CMB and with the observed abundances of light elements from Big Bang nucleosynthesis. Many candidates have been proposed: weakly interacting massive particles, axions, sterile neutrinos, and others. Direct detection experiments are trying to see dark matter particles scattering off nuclei in underground detectors. So far, no definitive detection. This is an open problem. If reality is a simulation, then the code has to include something that behaves like dark matter. It has to cluster gravitationally. It has to be cold, or at least not too fast moving, so that it can form the observed structures. It has to be almost collisionless, interacting mainly through gravity. It has to be present in the right amount to match the CMB, galaxy clustering, and lensing. That is a lot of constraints. If someone were faking a universe, dark matter is not a simple graphical trick. It is a consistent ingredient that shows up in independent data sets across cosmic time. Dark energy is even stranger. In the late 1990s, astronomers studied distant type Ia supernovae. These are exploding white dwarfs that reach a fairly standard peak brightness. Because of that, they can be used as standard candles to measure distances. By comparing their apparent brightness with their redshift, we can trace how the expansion of the universe has changed over time. The expectation was that the expansion should be slowing down, because gravity from matter should pull everything together. The data showed the opposite. The expansion is accelerating. Distant supernovae are dimmer than they would be in a decelerating universe. The simplest way to explain this within general relativity is to add a component with negative pressure, something that acts like a cosmological constant. This is what we call dark energy. It makes up about 70% of the total energy density of the universe today. It does not clump like matter. It appears to be roughly uniform in space and constant in time, at least within our current measurement precision. We infer dark energy not only from supernova, but also from the CMB and from the large-scale distribution of galaxies. The combination of these data sets consistently points to a universe that is spatially close to flat, with about 5% ordinary matter to 5% dark matter and 70% dark energy. This is often called the lambda CDM model, where lambda is the cosmological constant and CDM is cold dark matter. It is a simple model with a small number of parameters, and it fits an enormous range of observations. We do not know what dark energy is at a fundamental level. It might be vacuum energy, the energy of empty space. Quantum field theory predicts vacuum energy, but naive calculations give values that are many orders of magnitude larger than what we observe. This is sometimes called the cosmological constant problem. It is one of the biggest unsolved problems in theoretical physics. Alternatively, dark energy might be something dynamical, like a slowly rolling scalar field, or our theory of gravity might need modification on very large scales. We do not have a definitive answer yet. If reality is a simulation, dark energy is another non-trivial requirement. The simulation would need to produce an expanding spacetime whose expansion rate changes in time in a very specific way. It would need to transition from a matter-dominated decelerating phase to a dark energy-dominated accelerating phase at around redshift 0.5 several billion years ago to match the supernova data and the growth of structure. It would need to yield a universe that is about 13.8 billion years old, with a specific relation between distance and redshift that we observe in the CMB and in galaxy surveys. The cosmic expansion history is not arbitrary. We map it using baryon acoustic oscillations, which are relic sound waves from the early universe imprinted in the large-scale distribution of galaxies. These give us a standard ruler at different epochs. The pattern of galaxy clustering on scales of hundreds of millions of light years is sensitive to the expansion history and the contents of the universe. When we compare the data to models, lambda CDM with dark matter and dark energy fits remarkably well. Any simulated reality that tries to mimic our observations has to reproduce this specific pattern of fluctuations and their evolution over billions of years. Now, let me talk about spacetime itself. In our best-tested theories, spacetime is a smooth four-dimensional manifold with a metric that satisfies Einstein's field equations. Locally, physics respects Lorentz invariance. That means the laws look the same in all inertial frames. The speed of light is constant. We have tested Lorentz invariance to very high precision with particle accelerators, atomic clocks, and astrophysical observations. We do not see preferred directions or speeds in the fundamental laws. If reality were running on some discrete underlying grid, like pixels in a video game, we might expect to see tiny violations of Lorentz invariance at very high energies or very small scales. People have looked for such effects, for example, in the arrival times of gamma rays from distant bursts or in the dispersion of high-energy cosmic rays. So far, there is no clear evidence of such discreteness. That does not rule it out, but it pushes any underlying lattice spacing to scales much smaller than we can currently probe, likely below the Planck length, about 10⁻35 meters. The Planck scale is where our current theories break down. If we try to combine general relativity with quantum mechanics in a naive way, we get infinities. We do not yet have a complete theory of quantum gravity. Candidates like string theory and loop quantum gravity suggest that space-time might be quantized or emergent from something more fundamental. But these ideas are still under development and not yet confirmed experimentally. This is a genuine unknown. It is one of the deepest open questions in physics. In a sense, this is the closest place where the idea of simulation overlaps with mainstream physics. Many approaches to quantum gravity suggest that space-time and perhaps even quantum fields might emerge from some more abstract structure, like entanglement patterns or algebraic relations. That is not the same as saying there is a computer in another universe running a program. It is saying that what we call space, time, and particles might not be fundamental. They might be effective descriptions of something deeper. If that deeper layer is discrete or information-like, it can feel reminiscent of a simulation. But that is a metaphor, not an established fact. Let me ground this back in what we can observe. We map the large-scale structure of the universe by surveying millions of galaxies. They are not randomly scattered. They form a cosmic web of filaments, sheets, and voids on scales of tens to hundreds of millions of light years. This pattern arises naturally in simulations of structure formation that start from the tiny fluctuations we see in the CMB and evolve them forward under gravity in an expanding universe with dark matter and dark energy. These are numerical simulations we actually run on supercomputers. They are useful because they show us how sensitive structure formation is to the underlying physics. When we change the amount of dark matter or dark energy in these simulations, or alter the nature of dark matter, the resulting cosmic web looks different. The sizes of halos, the abundance of galaxy clusters, the thickness of filaments all shift. By comparing simulated universes to the observed one, we can constrain our cosmological parameters. This is a key point. We already simulate universes within the limits of our physics and computing power. We see how hard it is to match all the data at once. The fact that our real universe sits in a very narrow region of parameter space that fits all observations is not evidence for simulation. It is evidence that physics is strongly constrained. Those simulations also show us something about the fate of the universe. In a universe dominated by dark energy that behaves like a cosmological constant, the expansion keeps accelerating. Galaxies that are not gravitationally bound to us will eventually cross our cosmic horizon. Their light will no longer reach us. Over many tens of billions of years, the observable universe will become emptier from our point of view. The local group of galaxies, including the Milky Way and Andromeda, will merge into a single large galaxy. Star formation will slow as gas is used up. Over trillions of years, stars will burn out. Black holes will dominate. Over vastly longer times, even black holes will evaporate via Hawking radiation. The universe approaches a cold, dilute state, sometimes called heat death. This is not a story of meaning or purpose. It is a consequence of the second law of thermodynamics applied to a universe with a positive cosmological constant. If reality is a simulation, and the simulation is faithful to our current best cosmological model, then it must also simulate this long, slow evolution toward a nearly empty de Sitter-like spacetime. That is a lot of computational effort for a very quiet end. Again, this is not an argument for or against simulation. It is a reminder that any simulation hypothesis has to take real cosmology seriously if it wants to be more than a slogan. One might ask whether there are glitches in the universe, signs that the simulation is imperfect. In physics, we do look for anomalies. We look for deviations from our models. For example, there is a current tension between measurements of the Hubble constant from the early universe using the CMB and from the late universe using supernovae and other distance indicators. The values do not quite agree. This could be due to unknown systematics in the data, or it could hint at new physics beyond lambda CDM. It is an active area of research, but we do not jump to simulation error. We first look for mundane explanations, then for consistent modifications of our models that can be tested further. The same is true for dark matter detection experiments that see hints of signals that later disappear with better data, or for slight anomalies in the CMB maps that might be statistical flukes. Science is full of small discrepancies. Most of them are resolved without needing radical new ideas. A few persist and may point to deeper physics. None so far require us to invoke an external simulator. Another angle people sometimes take is to ask whether the universe is computable. In practice, the laws of physics as we know them are local and governed by differential equations. To predict the future exactly, one would need to know the initial conditions with infinite precision, which is not physically meaningful. Quantum mechanics adds intrinsic randomness to outcomes, at least in the standard interpretations. A simulation could in principle reproduce this randomness using a pseudo-random number generator or some other mechanism. But from our perspective inside the universe, the statistics of quantum events follow very specific distributions. We test those distributions in experiments like Bell tests, and they match quantum predictions. Any simulation would have to reproduce those correlations exactly, including the non-local correlations of entangled particles, while still respecting no signaling constraints. That is a non-trivial requirement. In cosmology, we treat the initial fluctuations in the early universe as a random field with a nearly scale-invariant power spectrum, as predicted by inflationary models. The specific pattern of hot and cold spots in the CMB is one realization of that random field. We can measure its statistical properties and compare them to theory. So far, they match a simple Gaussian random field with small deviations. This is consistent with a quantum origin of fluctuations during inflation. A simulation could generate such a field by drawing from the same distribution. But again, that is just another way of saying it must reproduce the same statistical structure we see. So where does this leave the idea that reality might be a simulation? From the perspective of cosmology and astrophysics, the key point is that any such simulation would have to implement a universe that, to an extremely high degree of accuracy, obeys general relativity on large scales, quantum field theory on small scales, contains dark matter and dark energy in the proportions we infer, produces a CMB with the observed spectrum and anisotropies, forms a cosmic web matching our galaxy surveys, and evolves into a future consistent with an accelerating expansion. It would need to respect Lorentz invariance at energies we have probed, reproduce the observed particle content and interactions, and match the detailed nucleosynthesis of light elements in the early universe. We do not see any clear, large-scale violations of these patterns. Our uncertainties live at the edges. The exact nature of dark matter, the origin and nature of dark energy, the physics of inflation, the unification of gravity with quantum mechanics, and the precise value of the Hubble constant. These are the places where our models are incomplete or under tension. They are not holes that obviously suggest an artificial overlay. They are opportunities to refine our understanding of the underlying laws. As a scientist, I treat the simulation idea as a philosophical overlay on top of physical models, not as a competing physical model by itself. It does not currently make testable predictions that differ from standard cosmology. If someone proposes a specific simulation framework that implies, for example, a detectable energy-dependent speed of light or a particular pattern of Lorentz violation, then we can test that. So far, we do not have such a concrete, widely accepted simulation physics model. What we do have is a universe whose large-scale behavior is remarkably well described by a simple set of equations and a small number of parameters, and whose small-scale behavior is governed by quantum fields that we can probe in accelerators and in astrophysical environments. We have a dark sector that dominates the mass energy budget and remains mysterious. We have an accelerating expansion that points to a vacuum energy problem we do not know how to solve. We have hints that spacetime and gravity might be emergent from something deeper, but no complete, experimentally verified theory of that deeper layer. So when I am asked whether reality might be a simulation, I translate the question into a more scientific one. I ask, are there features of our universe that force us to go beyond our current physical models? And could those features be explained by a more fundamental description that might look, in some respects, like information processing on an underlying structure? The honest answer today is that we do not know. We can say that any such deeper description must reproduce dark energy, dark matter, gravity, spacetime, cosmic expansion, and the observed large-scale structure with great fidelity. We can say that our current observations do not require us to invoke a simulation, but they also do not rule out the possibility that space-time and fields emerge from something more primitive. The open scientific question I end with is this. When we finally have a consistent, experimentally supported theory of quantum gravity that explains the origin of space-time, dark energy, and perhaps even dark matter, will that theory describe reality as fundamentally continuous or fundamentally discrete and information-like at the deepest level?